Hello Calc. I'm going to go through another delta epsilon proof. This one is quadratic. So far we've been working, at least on the videos, on linear ones. So quadratic one, I want to show that the limit as x approaches 2 of x squared is 4. 4 is the limit. Let me have a clock. Clock, clock, clock. I'll just use this. So it is 12:33. Alright, try to keep an eye on the time. So if the limit is 4, here's what we have to prove with the delta epsilon proof. If when 0 is less than the absolute value of x minus a is less than delta, so in other words, as we get closer in our choices for x to a, we are going to be within delta of a for our choices of x. When that's true, then this should also be true. So the function, in our case, x squared minus 4, the limit, when our values of the function should be within epsilon of 4 if 4 is the limit. So putting all these symbols into our problem, we will assume it's like greater than 0. So we're going to put in x minus, what's our a? It's what we're approaching. It's 2. So that is, if that's true, delta, then this is true. The function x squared minus 4 is less than epsilon. So we're going to try to find a rule, so no matter what epsilon I give you, you can give me a delta that will create this true statement, make this statement true, and if you can find such a delta, then you have proven that the limit is 4. So we always kind of work on this side and do our scratch work, and then we'll come in a forward motion and do the proof. So let's work backwards and notice that that is factorable to x minus 2, x plus 2. Which is nice. It's easier to work with linearity, with linear terms. So usually the quadratic expressions are factorable. And when we look at that, we see that there's an absolute product, an absolute value of a product, which is the product of the absolute values. So I can put an absolute value around each of those factors. So note, if we have a delta that works, any delta smaller than the delta we come up with will also work. Does that make sense? So here we have an expression. We're approaching 4, and we're expecting, no, we're approaching 2. And we're expecting the answer to be 4. And if we find a delta, so if we go up 2, and we get, from 2 we go 2 plus delta, and we go back delta from 2 minus delta. If we find a delta that always gets us within epsilon of 4, so we go 4 plus epsilon and 4 minus epsilon, if we find a delta that works, doesn't it make sense that any other smaller delta will also get us within the desired band? It does. So let's make a note of that. We're going to need that reasoning in a minute. If we find a delta that works, any smaller delta will also work. Alright, so keep that under your hat. You can see that this quadratic delta epsilon proof is going to take a little more reasoning than the straightforward ones that you've seen so far. So we have to make sure that absolute value of x minus 2 times absolute value of x plus 2 is less than epsilon from this line. So this is looking good because we're seeing the same thing over here. So that's looking good. So we want to hang on to that. And we want that to be close to 2 when delta is small. So, but what about this factor here? We can't just drop it, yet it doesn't seem to be part of what we're aiming for. So we're going to have to put some reasoning into this term right here. So, is there a way I can bound this? In other words, is there a way I can discuss the highest and the lowest that this can possibly be? I think so. So, as we squeeze delta closer and closer to 2, we are wondering, what if delta is 1? So, for delta equals 1, that's not squeezing so close to 2. That means we're going 2 plus 1 up, and then 2 minus 1 back. So if we say delta is 2, then this expression, x plus 2, oops, sorry, I'm looking at the wrong graph. I have to look at this graph. The graph of absolute value of x plus 2, y equals the absolute value of x plus 2, is going to be a straight line. And first of all, you graph y equals x plus 2, crosses at the y-axis and goes over 1, up 1. And it would go continue like that, but the absolute value part makes it flip up like that. So we're looking at this expression now for a moment, and we're bounding it. We're able to accept the fact that we can go up from 2, 1, and down from 2, 1. Because 1's a pretty good number, and it's still fairly close to 2. So over here, if we're keeping that delta equals 1, then we know the values around 2, if for delta equals 1, it goes up to 3 and down to 1. Now in that, what is happening to this function, this factor right here? Well, when I put a 3 into here, I'm coming out with a 5. When I put a 1 in here, I'm coming out with a 3. So I am finding that the highest possible value, if I say delta equals 1, the highest possible value that this expression can be is a 5, and the lowest is a 3. So this absolute value of x plus 2 is going to be along this interval between 3 and 5. All right, so keep that. Hopefully that makes sense and you can follow that. So if delta equals 1, and because of this thought, or is less than 1, so for delta less than or equal to 1, then we have a good situation. We have the absolute value of x minus 2 times the absolute value of x plus 2 is less than epsilon. But we know the highest this can be in a reasonable interval where delta equals 1 is 5. And we got that from here in this description. And then we can say x minus 2 is less than epsilon divided by 5. And so right here we're matching that. So we can say let delta equal epsilon over 5. And then it seems like we're ready to reverse it and go the other way. But there is a consideration that I have to make before I can be so bold. So what if over here delta is nice and small and it works and it gives us a good rule for our delta, epsilon over 5. But what if epsilon is large? So what if these small deltas are giving us a large band around the limit? Like suppose epsilon is 20. Then we come over here and we see epsilon is 20 divided by 5. So I'll put some thoughts here and then we'll probably erase them. What if epsilon equals 20? Then delta, which we now are saying is equal to epsilon over 5, will be 20 over 5, or 4. So, and we just said in this part that delta has to be less than or equal to 1. So it didn't work. So the way that we adjust that or address that fact is fairly, it's not tricky, but it's fairly understandable. So what we're going to do, given any epsilon, no matter how small, given any epsilon greater than 0, let delta be the smaller of these two values. It's either going to be 1, because we know 1 creates a situation around 2, and that creates a situation around x plus 2 or by x plus 2. And so 1 works fine, and we've seen that. Or we are going to use, so I'm going to put a little word in front of here, let delta equal the minimum, and I think that's usually written with a brace. The minimum in this box is either going to be 1 or epsilon over 5. So we're going to take the smaller of the two, and if epsilon over 5 is very large, then we're going to use 1. We know that works. If this, as epsilon over 5 is smaller than 1, we're going to use that. But either one will allow us to go through this reasoning. So when we pick the smallest in this box, it's either going to be 1 or something smaller than 1. This is going to be smaller than 1 if we choose it. All right, if epsilon over 5 happens to be greater than 1, then we're going to let delta equal 1. So that's the way we jump over that problem. All right, let's go over here and do the proof in a straightforward manner. And you may not have even noticed at the end here where we had delta is epsilon over 5 that we even had to consider large epsilons, but we did. So we had to be thorough and experience much rigor. So let's go in the forward direction. So now we're going to start with this side and see if we get that side. If we do, then we know that it is the limit. 4 is the limit. So I'm going to say the absolute value of x minus 2 is less than delta. I'm going to say let delta equal epsilon over 5. So then I get the absolute value of x minus 2 is less than delta over 5. And I'm going to multiply both sides by 5. But this 5 is nice because I know that this expression, 5 times this expression, is less than epsilon. But I also know this expression, x minus 2, will never be greater than 5. So I'm going, first of all, I'm going to, never mind, I left the step all out. So I'm going to write x minus 2. Oh, I know, never mind, I'm explaining that wrong. So now I'm going to put a factor in here that compares to 5 in this way. The factor I'm going to add for the 5 is the absolute value of x plus 2. So this factor at 5 is going to be replaced by absolute value of x plus 2 because I know from my previous discussion this will never be greater than 5. It'll always be 5 or less. So can I not take an expression that I'm claiming is less than some number and replace it with a number that is less than this one and still get an expression that's less than e and epsilon? So I hope that makes sense why I can put that in for 5, because it keeps this less than true, because I know this is smaller than this or equal to. All right, so now I am ready to multiply those together and put it in one absolute value sign. And now we have finished QED, that which was to be proven. All right, so you can see that we have gotten to the spot starting with this and ending with this. A few steps, we had to do a lot of work to get down this few steps. All right, so that's how you do a quadratic one, and we'll give it a try when we get to those. These are advanced. These are advanced thinking, And thinking outside the box of the linear box,